you've done labs a few times, 3 or 4 times, right? So you would know what a data sheet is. You'd be working with voltages, currents, etc. So this is the time in the class when you have a feeling as to what is happening. When you say ones and zeros, they're nothing but voltages, currents. This semester, unfortunately, I'm not able to give you that, but stay with me. That I'll try to give you a flavor as to how do these chips actually work and why do we use certain chips over certain other chips. Okay. So let's talk about the first thing as to what is a logic family, right? So whenever you say something which is a logic family, you're basically saying how are the gates made? So you're asking the question, how do I make these gates? Remember, whenever you think about a digital system, right, always think about it in terms of hierarchical, right? So as you keep reducing the hierarchy, ultimately you get down to gates, and the gates further down you get down to transistors, right? So remember when we initially did AND gate, what did we say? One way to think about the AND gate was this, right? So I'll say that if I talk about the light, right, I'll say L implements A and B. That is, current will flow through this resistor only when my switch A and my switch B are closed, right? And this is how I implemented the switch model of an AND gate. Similarly, you guys have looked at our models of an OR gate, of a NOT gate, of an NAND, NOR, etc. Right? So these switches in real life are implemented using transistors, right? So you typically have transistors and resistors whenever you think about implementing these gates in physical silicon, right? Previously, you guys have come across another switch in ES. Do you guys remember the simplest switch? What was a simple electronic switch? No, no, not BJT. Before that,
Diode.
diode, right? What the diode was a simple switch in the sense that it allowed conduction only in one direction, right? And in the other direction did not allow conduction. So it was a one-way switch. So the oldest technology normally which was implemented in gates was known as a diode transistor logic. And you had what is known as RTL transistor logic, which is resistor transistor logic, right? So whenever I talk about logic families, I'm talking about how have I implemented that particular gate on silicon, right? In hardware, how have I implemented the gate using electronic devices? And so why is this important? Because this immediately will now dictate what are the voltage levels that can be used. This will dictate the speed of the circuit because ultimately the speed is going to be determined by what is the device you've used to implement that particular logic, right? So you begin to see that when you think about logic family, that gives you an idea as to what to expect when you're going to implement this on a board or you're going to implement this. So normally when we build circuits, first thing what we do is we wire it on a breadboard, right? So you wire it on a breadboard, right? And then also once your breadboard, you've confirmed your design. So breadboard is your first, what do you say, scratchbook on which you implement the design. Once the breadboard, you've demonstrated that your circuit works, then we put it on a board, right? A PCB board, which is what, if you open up any of your computers, you see the big board in green color, right? And that's essentially where your breadboard will eventually, the circuit on your breadboard will be eventually transferred onto that. And then you solder your chips or electronic components onto the PCB. The PCB has metal lines drawn on it, and that's how you build your system using building blocks, which are nothing but ICs, right? So ICs, discrete resistors, discrete capacitors are typically used whenever you want to build a system, right? So Aditya, PCB means printed circuit board. PCB stands for printed circuit board. Okay. Nishant, you're saying we can use resistors to implement gates. Well, not resistors by themselves. Resistors in combination with transistors are used to implement gates. Okay. So again, In this class, I'm not going to scare you with circuits because that will be specially reserved for the triple E students. But here, what we'll do is we'll try to give you a flavor as to what happens in a logic family. So why do we care about logic families? What is important? Why should I know this, right? And the reason you need to know this is, remember, when you're doing a digital design, you won't be able to implement it all as in one chip, right? So when you think about, say, somebody like we have something known as a SoC or a system on chip, right? So when you buy any of those big chips from NVIDIA, from Intel, or even Google nowadays, right? They make their own chips, which are basically the brain of the system. But in addition to that, you have to connect memory. Addition, you have to connect, say, some Wi-Fi components. Addition, you have to connect input-output pins, etc. Right? So even though some part of it can be put inside a silicon, eventually you have to go on a board, right? And so normally you're talking about a system. When you design a system, you're talking about a system which can have more than one integrated circuit in it. So when you're talking about something which has more than one integrated circuit in it, you're talking about a way in which these two ICs have to talk to each other, right? And as I told you, the logic family dictates what is the voltage level, what is the current level, etc. So it is very important that you know the logic family, because that kind of helps you design your system, right? You'd pick all chips from a given logic family so that they're compatible with each other. The good part is there are also certain chips available which can serve as interfaces, right? Next semester, when you guys do microprocessors and interfacing is a part of the course, right? So whenever you're dealing with the system level where you have to talk about building a system which has a microprocessor, which has certain input output nodes, which has memory, a large part of the course will teach you how to interface these different chips together, right? And so interfacing is again an important um, what do you say, component when you're designing the system. That is, if you have two chips which are designed on different logic families, you need to think of, okay, I might have to translate the voltage level up, or I might have to increase the current driving capacity of these individual lines, because a voltage of 2 volts can mean a 1 in one family, can mean a 0 in the other family, right? So depending on which family you choose, the definition of what a 2 volt means can change. So therefore it's very important to keep your families together and keep them all designed from a single family. Okay. So as I mentioned, the oldest family was diode logic. That is where the gates were built purely using diodes. Those of you who are taking ED will appreciate later that by the end of this month, that diode is one of the simplest device to manufacture. So generally diode logic, before you make transistors, making something on diodes is very easy. So that's why diode logic came first. And then they moved into resistor transistor and diode transistor. So these were some of the old technologies. They're obsolete now, primarily because nobody uses them. We've come up with transistor level families which are able to get away. We are able to get away with better chips, right? So the next big group of chips are the TTL logic. And so TTL is primarily what we use in our labs today. So most of our chips in the lab are essentially TTL logics. And how do you identify a TTL logic is basically the chip number begins with either a 74 or a 54, right? So whenever you see chip numbers beginning with either 74 and 54, you should assume that it is from the TTL family. And so the TTL family is nothing but we use transistors. So that is the number of resistors are reduced in this circuit. And there are different flavors of TTL logic. And the reason these different flavors exist, we'll talk about it towards the end of the lecture, is that they have slight differences. For example, you have your standard TTL logic, right? But you also have a variations in terms of the power consumed. So you have a low power version of it and you have a high power version of it. And whenever you say something is, so you might ask me, sir, what is the point in using high power version? Anybody want to guess? Why would I use a high power version if there is
So
a low
speed.
power? Exactly. So almost always, right? And when I show you the data sheets of these, you'll see almost always you will spend more power if you want things to switch faster. So therefore, speed and power generally go in opposite directions. So many a times in electronics, you'll always see that the electronic manufacturer will give you a slew of options. He'll say that, okay, you have this low power option, you have a high power option, and you have a standard option. Pick and choose depending on what you want to do. Right. Then you have other things known as shortcut ATL. Again, those in electron devices will understand all these later in the semester. So shortcut TTLs are faster versions of regular TTLs. So generally, you'll see that shortcut TTLs will have much faster switching speeds than the regular TTL logic. And you also have other versions of low power and fast. So again, we'll talk about some of the features of these. Again, I don't expect it to know how to design all this. Nobody's expecting you to know all that in this class. I just want you to appreciate the fact that there are different families available. So whenever you want to build a system, you need to pick and choose from the right family. So in the design assignment, right, it depends again on what you want to when you want to design something, I would expect that when you list out what are all the different chips you're going to use, you would ensure that they're all picked from the single logic family. And if they are not, then you will ensure that you put the right interfacing if you're mixing chips between different families. So this is giving you a further level of abstraction, right, as you're doing your design. So Sarthak asks, what are those numbers? Again, these numbers in the parentheses, these are how the chip now. So if you buy a standard TTL chip, it will start with number 74. So these are how the chip numbers. This is the naming convention for the chips when they're made in this technology. So you'll see that, for example, remember when I showed you the chip for if you look at the NAND chip is 7400. So 7400 essentially means it's a TTL logic and it's a standard TTL logic. So if you go up and look into the folder where we have uploaded all the data sheets of the various gates, you'll see most of the gates that we use in this class, most of the chips that we would have used if you were in the lab on campus would mostly begin with the number 74, indicating that they're all TTL chips. So TTL chips are very cheap, so you can get them pretty dirt cheap on Amazon if you want to look up, right? Yeah, so there to identify exactly. That's the convention we use. The other important technology is the CMOS technology. So again, you have CMOS chips available, and they normally begin with 4000. So if you find a chip which begins with the number 4000 or A or B, they generally tend to be MOS-based, CMOS-based chips. And because of the fact that their TTL chips are so prevalent, right? CMOS manufacturers also make pin compatible. So remember, ultimately, what does your chip look like? Ultimately, your chip should look something like this with a bunch of pins, right? These are your input output pins. So normally, if you look at TTL logic, it has 14 pins, 7 on each side, right? So if you want to design a system, right, sometimes you have different circuit boards. You've already pre-made your circuit board. So if you're going to now plug in another chip which is equivalent to this, so CMOS manufacturers also make chips which are numbered as 74C or 74HC. These are CMOS chips which have the same pin configuration as TTL. So these can be used in place of TTL in case you feel that that is something you want for your system. Okay. Harsh will talk about all the differences later. Okay. And finally, another very popular technology which is used a lot is emitter coupled logic. And this was designed at Motorola. And now On Semiconductor makes these chips. So these are the fastest chips. So generally, if you want a very fast design, you would use ECL chips. And ECL chips, again, couple of subfamilies for the ECL chips are the Meckel 10K, Meckel 10H, and Meckel 10E. So again, if you go out on Google and look for these chips, you'll be able to look at the data sheets pretty easily. So the one thing I want to focus on, and which we will do probably in the lecture on Fridays, I'm going to teach you how to do CMOS design. Why? Because this is the way most integrated digital circuits are designed. Right. So if any of you want to work in digital circuit design, then integrated digital circuits are basically almost always done using CMOS. So we'll give you a flavor of how to design CMOS based circuits. Okay. Again, it won't be a lot mathematical. The mathematical part will be dealt with in electron devices and microelectronic circuits. But here we'll just give you a flavor as to how to design. Okay. So let's first understand some conventions, right? So remember, whenever you're dealing with gates, you normally have currents and voltages associated with it, right? So whenever I'll see a gate which has a current flowing out of the gate, I'll call it positive. When I have current flowing into a gate, I'll say it's negative. So these are just conventions we normally use. Again, we'll talk about what these IOH, IIH, what do they all mean in the next few slides, right? But just now, so the reason why I'm telling you this is now if you go and open a data sheet, right? Again, go to okay, a good recommendation I have for all of you is when you get a chance anytime this week, go and look at all the data sheets, right? Once we've finished with this class, hopefully that will give you some idea as to what the data sheet is talking about. And it'll also help you later when you're designing anything. So let's look at,
So in out is
yeah, go ahead.
positive or negative? I didn't get that.
So if current is flowing into a gate, right, I will call it as positive current. If the current is flowing out of a gate, I'll call it as a negative current. Okay, why
Okay,
is it
got it.
positive, negative? For that, you need to understand the design inside the gate, which unfortunately this class will not go into. But when you do, if you're an A3, A7, AA or an A8 student, you'll get to learn it in ADVD as to why current flows in and current flows out of certain gates. Okay. Okay, so let's think about what are all the different parameters. So when you talk about digital design, what are all the electronic parameters that one needs to think about when you're looking at uh, digital circuits, right? So this again, remember now we're going to talk about physically measurable parameters like voltages and currents and time delays, frequencies, etc. So no longer ones and zeros. Okay. So the first thing to keep in mind is what is known as an, so again, remember, whenever you say digital logic, right, we're going to talk about what happens at 0 and 1. And remember again, 0 and 1 is for a positive logic. So remember when I discussed positive logic and negative logic, in reality, what we're talking about is a low and a high. And this is purely voltage driven, right? So we talk about two states of a gate. One is a high voltage, one is a low voltage. When we say positive logic, we map the high to 1 and we map the low to 0, right? If I'd using negative logic, then I would map the low to 1, right? So when you do active low circuits, remember a decoder, you can have an enable that is active high or an enable that is active low, right? So when I say there's an active low enable, it means that the chip will work only when the enable signal goes low. So it is normally shown with a bubbled input. Whereas positive logic will not have a bubble, it would just be a standard connection into the chip, right? So when I talk about a term which is known as IIH, right? This is the current flowing into the gate, right? This is, so again, I is stands for input, H stands for the state at that node, right? So IIH is the current flowing into the gate when I've applied a high voltage to that node, right? And again, remember, I'm not saying 0 or 1. 0 or 1 now depends on whether using positive logic or negative logic. And that's a flexibility you as a designer have. So if you go and again recall a couple of data sheets we looked back in the class, data sheets always quote high and low. They do not quote they do not quote zeros and ones, right? And that's a choice you make. Normally, most of us, to keep our sanity, keep map high to 1 and low to 0, because that way we don't get confused between voltage numbers and the logical meaning of that. But there is no limitation that you have to do it that way. So again, IIH, IIH is the input current into the gate when the input is a high voltage, right? And the same logic you have an IIL, which is the input current when you have a low voltage. So again, remember, at any node, you can have a high voltage or low voltage, right? Those are the two states available in the digital system. We are talking about digital systems which are two-state digital systems, so or two-state Boolean algebra, right? We are looking at the simplest form of Boolean algebra, which is a two-state Boolean algebra. So in that, we talk about two states, high and low. So at both these states, have different currents which are flowing into the gate. So again, remember, just because voltage is high and low doesn't mean current is equal. Current is also different between the high and low voltage, right? So what this means is when you're going to design the circuit, you need to also ensure that you're flowing in this much current, right? So as a circuit designer, when you're designing your board, it is not enough that you just apply a voltage. The source, the voltage source that you've applied at this pin should be able to also source this much current out. If the voltage source is not able to give you this current, then the IC is going to malfunction. That's because it's not able to hit your IIH or IIL requirement, right? So in addition to voltages, remember currents are also important, and this is true especially in the case of TTL logic, because TTL logic is based on BJTs, and as most of you know, BJTs are current controlled current sources. So a BJT tends to be very sensitive to the input currents. So you'll see that in TTL logic, this is a very important requirement that you must satisfy if you're going to use a particular chip. So in the same logic as what happens at the input, right? So here, if you look at this, at the input, I was saying that there is an IIH and an IIL. Similarly, at the output, you have what is known as an IOH. So this is the current flowing out at the output, right? When the input conditions are such that there should be a high level at the output, right? Or when the output node is a high, then the current flowing out of that gate is known as IOH, right? And we'll look at some numbers. So basically what normally happens is that the output current is normally much higher than the input current, right? So if I'm taking a special case where the output IIH is 400 microamps, right? And if I say that the input current is only 40 microamps, that means I can take 400 microamps and give it into 10 other gates without affecting the logic value at that node, right? So these 400 microamps can be split across 10 gates where I supply 40 microns to each and every gate. So then the logic high stays logic high, and I'm able to give the output of one gate to the input of 10 gates, right? So when I've given an output, when I've given a ratio of 1 to 10, that is, I've taken the output of one gate and I've fed it into 10 inputs. So I can say that the fan out of this technology is 10, because I can take the output of one gate and feed it roughly into 10 gates without losing the value of high, right? Neil, you're right. We'll talk about the voltage ranges in the next slide. Right. So similar to so again, remember, you have current levels associated with high and low at both the input and the output, right? So depending on, so it's not only voltage that you need to satisfy, you need to satisfy the current requirements of the gate if you want that gate to function according to its data sheet. So similar to that, we'll now talk about the voltage ranges. So again, remember these are some of the key voltages. When you look into a data sheet, you guys can go and look at so one thing I would also suggest is, if you want, you can open up a data sheet on another window and look at it as we go through, or you can do it after the class. So remember, when you talk about digital logic, if you remember long time ago we discussed, suppose this is your maximum voltage range, 0 to 5 volts, right? If that is your maximum voltage range, right, then we know that if I give 5 volts, it is a high. If I give 0, it's a low. But I also mentioned you normally end up having ranges, right? You have a certain range which you can say that if the voltage is in that range, I will consider it a high. And if the voltage range is in around 0, I'll consider it a 0, right? So we'll talk about that right now. So if you look at so we talk about what is known as a VIH, right? So remember, again, when you look at high, right, the maximum high voltage can be the supply voltage. So in TTL logic, in most of the chips that you'll work in the lab, they're normally targeted for a 5-volt operation. So which means that the input voltage can have a maximum value of 5 volts if it has to be in the high state. But we talk about what is the minimum voltage that can be present at that node for it to be still counted as a high, right? And that is known as VIH, right? So VIH is the minimum voltage that should be available at a node for it to be called as a high state, right? And in TTL logic, this number works out to around 2 volts. So you'll see that as long as your input voltage is between 2 and 5 volts, the input looks like a 1 or input looks like a high, right? So any voltage in the range between 2 and 5 in TTL logic at the input will be treated as a high state. Okay. On the other hand, as I told here, the minimum value of the input voltage for low would be 0. But there is a certain value up to which I will still call it a 0, right? And so that is denoted by VIL, right? Again, this is at the input side of the gate. And VIL denotes what is the maximum voltage I can apply at the node, and it still can be treated as a legal low level, right? So this is, again, so remember, my input at the input, my if I have to be in a high state, my input voltage should be between VIH and the maximum voltage, which is 5 volts in TTL. In the low level, if I have to show a legal low at the input, then my voltage has to be between 0 and VIL, right? And so in TTL logic, this number is around 0.8 volts. So you see that the band for high in TTL is much higher than the band for low, right? And similarly, like how we have at the input side, you also have same voltage requirements at the output side. And so at the output side, again, VOH is the minimum voltage at the output, which counts as a output high, right? And again, these two don't need to be equal. See, the other point I want you guys to remember is that VIH needn't be equal to VOH. And why is that? Because VIH might be at the base of the transistor, VOH might be coming from the collector of the transistor, right? And so there are different semiconductor devices associated at which node you're pulling out the output from. So generally what we see is that in TTL logic, the VOH is around 2.4 volts. And similarly, VOL, which is the maximum value of the output, you can allow for it to be in the low, right? And that is roughly 0.4 volts. So again, you see this mismatch between input and output, especially in the case of TTL, where input voltages between 2 and 5 are treated as high, but output voltages only between 2.4 and 5 are treated as high. Okay. Now I'll just take a couple of questions. So Harsh asks, if the current enters IH as 40 microns, how does the extra current? So IH is a minimum requirement. The gate will be able to take anything more than IH, but it has to, you should at least supply IH to it. If you don't supply IIH to it, then it won't be a valid high, right? So if the current is greater than 40 microns, nobody cares, but the current cannot be less than 40 microns.
So can it be less than 400 microns in IO?
It cannot be less than 400 microamps in IO, right? It has to
So
be.
IH should also be greater than 400, right? Because the current will not come from anywhere else. It has to come from IH to IO.
Sorry. Yeah, so when you look at IOL, my apologies. When you look at IOL is the maximum value of current and IIL is the minimum value of the current. When you look at input output, it's maximum and minimum. My apologies. So Sayam, hopefully that answers your question also. Okay. Again, think about it, right? This is how you think about. So suppose I take a NAND gate and apply a 0 at both the inputs, right? Then I know the output has to be a high. So which means that this NAND gate is going to give out a current which is IOH, right? And a voltage which has to be greater than VOH. And if I apply it to another NAND gate, then it has to ensure that this current is at least IIH and this voltage is at least VIH, right? So whatever else you connect in between should ensure that these levels are not missed, because that means if these levels are not missed, if these levels are missed, that means even though this NAND gate is giving a 1 at the output, this NAND gate doesn't see the 1 as the input, right? So hence this matching is important to understand. And so from that also the values of fan out flow out, right? Similarly, if you look at the low, if I give a 1, I tied the NAND gate and give a 1. Remember, tying two inputs at a NAND becomes an inverter, right? So if I give a 1 at the input, then these are the ways the currents will flow, and that's the voltages. So Akshat, we'll talk about that just a second. Okay. So the third delay, and this is something that now you will start with Verilog in the next week, right? We'll come upon this time and again. Is that what is known as the propagation delay of the gate? So propagation delay of the gate is the time delay between the change occurring at the input to it being reflected at the output, right? So this assumes that whatever change you're making in the input will impact the output, right? So propagation delay is defined only when the input and output both change. If the output is not changing, then there is no concept of a propagation delay. Okay, okay, I'll just go 1 second. Somebody wants to see the previous slide. What was the wire coming down? So this wire is now, I'm just showing where the ground is. Because remember, when you talk about a potential difference, right? It's a difference. So this is your reference ground. So when you've implemented this in the IC, you would have a VCC and a ground pin, right? So this is that ground pin. This ground has just been shown so that I can tell you what that voltage is in reference to, right? So it is with reference to that particular ground on that IC. All right. So remember again, propagation delay, right? I mean, it's an important concept that input change to output change, right? For example, suppose you think about an AND gate, right? And suppose I've given one input as a 1, right? And I call this input A, right? So when A is a 1, right? I know the output is a 0. When A switches from 1 to 0, right? This is how I denote a switch. When A switches from 1 to 0, then my output switches from 0 to 1, right? And so the time difference between this to this gives you the propagation delay of the circuit. However, if this was a 0, say, right? So if this was a 0, what happens to the NAND gate output? If this was a 0, the NAND gate output is going to be 1 at all times, independent of whether A is a 0 or 1. Everybody with me? Right? Because if one of the inputs of the NAND gate is a 0, that means that the output is always going to be a 1, right? And so what happens is, even if A switches here, right? Even if I switch the value of A here, Y is not going to change. So in this case, I don't need to worry about the propagation delay of this gate, because as long as one of the inputs is tied to 0, output Y does not depend on A, right? So whenever we talk about propagation delay of the gate, you need to talk about the conditions only when a change in the output is reflected by a change in the output, right? So this input to output both have to change for you to define what is the propagation delay of the gate. Okay. And in the most generic case, right, what happens is that, again, this is something you'll understand when you start learning about transistors, that the speed, for example, we talk about two kinds of transistors, NMOS transistors and PMOS transistors. One is an one is a transistor that works with electron current, one is a transistor which works with hole current. So some of you know electrons move faster than holes. And so what happens essentially is that the NMOS transistor tends to be faster than a PMOS transistor. Or an NMOS transistor can conduct more current for a given voltage than a PMOS transistor. So therefore, there is already a mismatch happening when you use an NMOS transistor or a PMOS transistor. And so you see that the propagation delay similarly has a difference. So if the output is transitioning from low to high, it might have a different delay as opposed to the output transitioning from high to low. So we talk about two propagation delays, a TP-LH and a TP-HL, right? And both these are related to the output only. Remember, LH is when the output transitions from low to high, and HL is when the output transitions from high to low, right? So normally when we talk about TP, we'll take the average of these two and give it as a TP, or we'll take the worst case. So if you're a cautious designer, I would say my TP is going to be maximum of TP-LH, comma TP-HL, right? Because I want to ensure that I'm not making any mistakes ever if I'm just going to use TP. Or I might say, okay, I don't care, I might have some issues, but let me just take it as the average. So this is for an engineer who's willing to accept some errors in the circuit. But if you're going to be a cautious engineer, you would ensure that you'll take the propagation delay to be the worst case delay in your circuit, right? That way you ensure that the circuit will never fail. Right, so this is how normally you measure the propagation delay. So suppose this is my input, right? And I have two outputs. I have an output which is coming out in phase to the input, and have an output which is out of phase from the input, right? Again, remember phase, 180-degree phase, right? So when it's a 0, this is a 1, vice versa. So I talk about my TP-LH as the propagation delay from the input. So normally I would start with 50%. So where the voltage, so remember these are voltage curves in case you're plotted voltage as a function of time, right? So this is the point in which it is 50% of the voltage to the point when it becomes 50% at the output. The time delay between these 2 points is TP-LH, right? And similarly, the time delay between these 2 points is TP-HL, right? And vice versa. Here it would be TP-HL first here and then TP-LH here, right? So depending on what you're measuring, normally we do the 50% to 50%. So here I'm measuring delay from 50% input to 50% output. Okay. So that's how normally when we talk about propagation delay, this is what we mean. So it's a measure of the speed of the gate. And remember that all gates have certain propagation delay. So combination circuits are never instantaneous. And it actually helps us because we have a lot of very cool circuits we can design, what are known as pulse shaping circuits. So I might give you, let me think, I'll probably put something in the tutorial. So pulse shaping circuits, right? You basically use the delay of the gate to start generating pulses of given duration, right? So you can design a circuit which can give a particular duty cycle depending on what the delay of the gate is. And the advantage of such a circuit is it's less sensitive to external conditions because it only depends on the propagation delay of the gate. You can end up creating a much accurate circuit for a given duty cycle. So I'll think of some examples for your tutorial in the next week. Okay. Now let's list. Okay, out of phase we do this, right? Suppose I take this point and I will take this point, and these two will essentially become TP-HL for this output, right? And similarly, this would become TP-LH for this output, right? Manav, I will take an example in next week's tute and we'll discuss that. So in this output, the output is going from high to low, no? So this becomes a TP-HL. And here the output is going from low to high, so it becomes a TP-LH. Remember, LH and HL are always with respect to the output you're talking about. So in this output, it is TP-LH. In this output, it is TP-HL. Okay. Remember again, so if I've not made it clear, right? Propagation delay for any circuit is always given for a particular input output combination. Right? In a gate, it's easy, but even if you start thinking of large gates, which have like 4 inputs and 1 output, right? Then it is important that you design, when you talk about propagation delay, you specify which input to which output. Or in other words, normally what we do is, suppose there are more than one input, suppose there are 4 inputs, for example, I will call propagation delay as the longest delay. So I'll measure the individual delays between every input and every output. And then I'll say that my propagation delay is the largest among all these 4 delays, right? That is how I will tell you that is your worst case time. So this is the time you must give the gate for it to give you a valid output. So that is normally how I define a propagation delay for a multi-input gate. Okay, Manthan, again, let me repeat. Whenever you measure time differences or time delays, right, you need 2 points, right? Suppose I have a pulse which looks like this, right? And I have another pulse which looks like this, right? How do I define what the delay between the two pulses are? So normally what I do is I will take a common reference point. I'll say 50% of the voltage, and then I'll measure the time difference between these two and say this is my delay between the two pulses. I could have also taken this point and this point, or this point and this point, right? But generally the convention is to take the halfway point between the two. Okay, exactly, Abhishek. Normally when we define propagation delays, we define it from 50% to 50%. You will see that certain designers use 10% to 90%, etc. I don't want to confuse it right now. There are other definitions for propagation delay also, but the simplest definition we talk about is 50% input to 50% of output. Okay. Okay. What other parameters do you have to think about when you're thinking about a logic family? Right. Remember also, if you if you recall, when I had shown you one data sheet, right? The data sheet has, if you take about any IC, it has a VCC pin and a ground pin, right? Because any IC needs power for it to work, right? And that power is coming from the supply that has been connected, right? So to get your digital IC to work, you need to connect it to a power supply, and that is going to supply power to your chip to give, which then performs your logic function that it's doing, right? So when you look at the supply, so we talk about what is known as a supply current. That is the total current that is being pulled by the logic gate when it wants to give you an output high or an output low. So sometimes you'll also see numbers as ICCH and ICCL. So ICCH is the current pulled from the supply when the output is a high. ICCL is the current pulled from the supply when the output is a low. Now, why is this important? Because this is a measure of the power, right? So if you have a high ICC, it means that your gate is consuming more power to give you that particular logic function. Remember, power in any integrate in any electric circuit is given by V cross I, V times I, right? So if my I goes high, it means that my gate is consuming more power. And so if power is something that you care about, you'll find the logic family which does not have very high ICCs. And therefore, the other thing I just alluded to would be power dissipation. So we normally also look at what is known as power consumption per gate. In addition to ICC, I'll talk about that how much power is consumed per gate. Again, this defines your overall power envelope. So many times when you're designing a system, say you're designing a handheld system, right? You would have a power envelope. So your customer would say, okay, at no point should the power consumed be more than say, if you talk about any chips which are on the iPhone, you have requirements as 1 microwatt or 100 nanowatts, which means that the power consumed in that module should never exceed 1 microwatt. So that gives you the power envelope. You normally design such that you meet the speed requirements while keeping the power below the power envelope that has been given to you, right? And that's the common design technique. So the third thing we talk about is, so remember, as some of you had appreciated earlier, speed and power are normally traded with each other. So many times we talk about a speed power product, right? Because some technology might seem much better if I'm able to give it more power. So if I want more speed, I can supply more power, right? So I always know I can trade off speed for power. But if I want to compare two logic families, how do I compare them? So another figure of merit to do that is basically using a speed power metric. The FOM stands for figure of merit, by the way, right? So this is normally used when you have to compare different logic families, right? So you want to see if my low power Schottky is it better than my standard TTL. I will look at the speed power product, because that gives me, because I have, as a designer, I have some flexibility where I can trade off power for speed. But even if I use all those flexibilities, does that give me the best power envelope, or do I need to move to a different logic family so that I can get the best speed for a given power, right? So the speed power product is a figure of merit that you use normally when you want to compare across different transistor technologies. And finally, another important thing we care about, which we've looked at before, is fan out, right? And fan out basically means that how many gates can I connect the output of my single. So suppose I have gate G1, right? And G1 has some output. How many gates can I connect this output to without it losing? Suppose this was a 1. I don't want these gates to look at 0 or some nonsense value here, right? So I want to always ensure that my value, when it's 1 here, the same 1 is reflected here. And so there is a maximum. There is a maximum of how many gates can be connected to the output of a single gate before the logic value at this node disappears. Right? And so normally that is known as a fan out. So Tanmay asks, speed power product, why don't we use a ratio? Well, because speed and power are inversely proportional to each other, we like to use a product. If speed and power were in the same direction, I would use, then there's no optimization. Na? Tanmay, the optimization occurs because as I increase speed, I reduce power. Sorry, as I increase speed, I increase power, right? And so when I want an optimization, normally I will do speed times power. Okay. Uh, Prayas asks, can you repeat what fan in was? Okay. So fan out, everybody understands, right? Now fan in is, normally when I say fan in, it means how many inputs can be connected to a gate, right? Suppose it's a 3 input gate, it means the fan in is 3. So fan in is not something that is in your, as a designer, that's not something, that flexibility you have, right? Because fan in is something which you have designed for. So if you're buying a chip, right, the chip already gives you a certain fan in. But what the fan out tells you is, okay, how many such chips can I connect my output to? So if I'm able, so you can imagine that if I have a high fan out, that means that I can reduce the size of my design, right? If not, I'll have to figure out other ways by which I can design the circuit, right? So having a fan out, many a times high fan out helps us design simple circuits, because I can take that output and use that for other things. Okay. So the last thing, and this was something I think somebody asked earlier, and I don't recall the name, I'm sorry. But let's now talk about what is noise parameters. So as you all remember, there was a mismatch between the input and output voltage levels, right? So remember that the input voltage level for high was different than the output voltage level for high. So let's look at the output. At the output, I define what is known as my VOL, right? And VOL is the maximum voltage at the output below which I say it is a logic 0, right? So if I have a voltage at the output which is greater than VOL, means that it is junk. I can't call it a 0, right? And I have a VOH, which is the minimum value of voltage I can get here for me to call it a logic 1. So what you see is, if there is a voltage between VOL and VOH, it means nothing in digital logic, right? In digital logic, the gate will not know what to treat it as. So what will normally happen in things like this is, in your circuit, there might be some freak nodes which will do this, and that's a bad design sign. So whenever you design your system, you have to ensure that at no point should the voltage at any node in the circuit get into this regime, because that would mean that doesn't have a logical meaning, that voltage, right? Now let's look at the input side. So this voltage is sometimes known as a disallowed range. So you don't want voltages at any node, especially the output, to sit in this range. If I look at the input, I'll take maybe 3 minutes, guys, and then I'll wind up the lecture. So if you look at the input, again, as we looked at before, the VIL tends to be higher than VOL, right? So in VIL, it is more forgiving. So even a slightly larger voltage than VOL can be allowed as a logic zero, right? So what you're saying is that even if I get VOL, right? Suppose so this comes in terms of noise. What is noise? Noise is a random process, and it's a random value, a random voltage that can be added to a node. So what happens? Suppose I take the output of a gate and I'm going to pass it to the input of another gate. What this is telling me is my output voltage. Suppose I add some noise to it, right? If I add a volt, if I reduce, so noise can be either additive or subtractive. It's a random number, right? So it can either be I add noise or I subtract noise. So if the voltage at the out, if the voltage as I'm going from this output to this input, if the voltage falls below VOL, I don't have to worry about, because I know it will be in the valid range for the low. But I have the margin of this difference. So even if my noise is such that my input level stays below VIL, it will be still be treated as an L. So the difference between these two levels kind of tells me what the noise margin is. So I can tolerate this much of noise, voltage noise at that node, and still not lose the meaning of a low. Similarly, if I look at IH, right, the advantage of TTL logic is my VIH is much less than VOH. And therefore, what happens is that even if the voltage at the output due to some random noise event drops further, as long as it doesn't drop below VIH, my input at the next gate will treat it as a high, right? And so what you see is that you talk about two noise ranges, a noise high and a noise low, right? So these two are what are known as the noise margins in the logic family. It is my voltage at the output of one gate can reduce by NH, VNH, and still be treated as a valid high. Similarly, my output voltage at a low from one gate can increase by VNL and still be treated as a logic zero. So this is what is known as a noise margin, and this noise margin is an important parameter. So higher the noise margin, the better your design would be, right? So again, in TTL logic, this number works out around 300 millivolts. So it's a good buffer to have, especially when you have to design large systems. Okay. So with that, I'll stop here. I'll continue the rest of the lecture on Friday. Um, I'll take any questions if you have any. Exactly. So normally when you design Saksham, normally when you design a digital logic family, you will obviously design something such that the input range is smaller than the output range. That way you always get a noise margin. Right? Now the problem that you have to keep in mind is you don't want this range to become too narrow, because then what happens is that you don't have a clear separation between 0 and 1. So at some point you have to trade off between how much this range is to what the noise margin is, right? Having high noise margin is good, but also you want a good separation between 1 and 0. If you don't have a good separation between 1 and 0, then it's possible that 1 and 0 might, you lose 1 and 0. Okay. Nishant, I did not understand fan out. What didn't you understand? Can you come online, or can you unmute yourself and ask me what exactly you didn't understand in fan out?
Sir, I did not understand like the definition you've given in the
Okay.
previous
So
slide.
what is fan out, right? So remember, when you did design in Logisim, or when you've done design in the class, right? You normally take an output and feed it to the input of another gate, right? And you can take an output of one gate and feed it up to 3 or 4 gates, or any number of gates, right? So fan out tells you what is the maximum number of gates I can feed the input, feed the output of a gate, right? For example, if I say a fan out of 10, a fan out of 10 means that an output of a gate can be fed to a maximum of 10 gates without losing the logical value of that node. Am I clear?
So you're saying that the output will lose its power if we give it as an
To
input
11
to a
gates
lot
or
of
12
gates.
gates, yes. So as long
Okay.
as the number is less than 10, when I say the technology has a fan out of 10, which means that as long as my, if I'm giving my input to less than 10 gates, I'll be safe. If I have to give it to more than 10 gates, then it'll end up causing an issue.
Yes, I got it.
Okay.
Thank you.
Arjun, is three state gates? Yes, they are. We will talk about it on Friday. When we solved Mark's questions, used a truth table, but there are the faster methods. So Mihir, there is a question in the tutorial, right? Try and do that. That was a question from last year's midsem. I am not aware of faster methods, but it's more, but we can discuss this in the tutorial tomorrow. So the 6 variable mux function that I gave you, think about it. It's not, it was a question of the midsem from last year. As, yeah. Harsh, what is the difference between supply current being high or low? Is there no output when it's low? So that is the thing I want you to understand. Just because the voltage, the node is low doesn't mean that the node has 0 volts. Node can have some voltage. So whenever you say high and low in digital electronics, high and low is normally associated with both the voltage and the current, right? And so supply current, when I say ICCL and ICCH, remember this has been implemented in a circuit, right? So certain transistors are turning on, certain transistors are turning off. So the current which is being pulled from the supply depends on whether your gate is giving an output high or an output low. So in the most generic case, the supply current is a function of what the output of your gate is going to be. Avi, why is there a difference? Again, for that, I have to go into the circuit of the gate. Generally, it tends in TTL gates that the input is the emitter base junction of the transistor. The output is the collector emitter junction of the transistor. They tend to have different cutoff voltages. Therefore, the VIL tends to be different from VOL. Can current, Sahaj asks, can current flow through the gate backwards? I don't know, what do you mean by backwards?
So like in
Sahaj,
a direction which is not intended to be flown, like
no, no,
through
no,
a
no.
AND gate, but backward.
If I mean it can. If you look at the circuit design, it will flow, but that will be a wrong operation. So you don't want your gate to do that. So normally you'll see that currents will flow. That's why you have that IL and OL. Sorry, yeah, ILOL or IHOH, right? So the currents normally flow in the same direction as was intended in that diagram. You don't want the current to flip direction. That means that it's gone from high to low. Neil, the output given here is coming from a different input and we're sending it to some other input where we check noise. Exactly. Or the noise can come even, suppose you're connected and using a wire. Suppose you've taken an output of one gate and using a wire connected to the input of another gate, right? From two different chips. That wire which is hanging in the lab can also end up having a noise on it. Some noise can come from any, there can be a magnetic field and some eddy current will be set up and there's an extra current coming in. Anything can happen. So noise sources are many. So in circuit design, we normally talk about noise. We just say, okay, the voltage is fluctuating. What we know normally about noise is we normally talk about a spectral density of noise. So we have studied enough noise to understand that, or we know when we study noise that we understand, okay, this maximum voltage can be so much or the maximum current can be so much. So generally when we think of noise, we know what is the worst case voltage to consider. So that's what helps us design circuits. Otherwise, noise is a random process. Abhishek, how do we change input from high to low linearly as shown in the VT curve? It's not a question of changing. That's how the voltage normally looks like. If you're going to go in and do a circuit design, this is how your voltage will look like when you plot the input output characteristics. In reality, it is not linear. It is curved. It is curved right here and it is curved right here. And that depends on the transistor characteristics. Okay. So in a big circuit, Yash, in a big circuit, the voltage would eventually drop to discern. Yeah, so in that case, we'll do what are known as buffers. So Yash, and we use buffers to beef up the power at any node and we'll send it on. You're right, this is a problem. So when you do large circuits, you have to be especially careful about this. Priyal, yes, this shouldn't be too small is correct, but think about the case, right? Suppose I make this range too small, then what happens is that even a small fluctuation in the zero might end up pushing it into a one. Right? So you don't want this range to be much smaller than the noise margin, because remember, any node which is sitting at zero can sit at this voltage. Now, if there is enough noise such that it can jump across this disallowed range, then it becomes a one, right? So you don't want these two levels to come too close to each other also. So you want them to be separated so that the zero stays a zero, right? Avi, yes, the labs next week will be on Verilog. I already announced that on Canvas, right? So Shiny, please talk to Sarang about it. Dr. Sarang can help you. Sir, Saksham, can propagation delay be externally manipulated by changing temperature? Yes. So Saksham, can you come online and tell me how will you change? You've done ED, so you should know. How would you change how would you increase the propagation delay?
So by externally changing the temperature, the
I know.
propagation.
Which way will the temperature go?
Uh,
So if I tell you that delay is proportional to the speed of electrons, which way will that how should I increase the temperature?
Probably decrease the temperature.
Decrease the temperature, right? So there is a huge branch of electronics known as low power. So this was, I think, 20 years ago. People were actually looking at one of the ways to design faster electronics was by actually cooling. So just like how in the fridge you have the coolant flowing through in the older refrigerator, you had actually coolants on the outside which were flowing and they were pumping and they were removing heat. So people were actually thinking of designing microchannels in a chip where you also feed it with coolants and reduce the temperature. What ends up happening is this ends up causing more, like it takes a lot of work to cool down a chip. So eventually you don't gain anything. Whatever speed advantage you get, you're going to burn it in power. So ultimately, it ends up being not a great way to optimize the system. Right. So Parth, what it means is no matter where the V input is between 2 and 0.8 volts, it won't give an output of 2 volts, right? It gives an output between 2 or 5 volts. And that output depends on what else is connected outside. Right. So at the output node, if you have some other circuitry connected to it, that will dictate what is the node voltage at the output. If that output voltage is just connected to a simple resistor, then it will depend on what the resistor value is, right? So 2 volts is the minimum voltage that is available for high, but it can be in the range between 2 and 5. Okay. All right. I'll see you guys on Friday then. Thank you.